Let's talk about the 2024 WAEC Physics Practical. In today's video, my focus will be on the mechanics, and specifically, I'll be giving you an insight into the principle behind the mechanics question. Let's talk about the apparatus. You usually expect the following apparatus: a rotor stand, a spring balance, a beaker, water, masses, and another liquid labeled L. And you should expect that liquid to be kerosene. From this apparatus, it can be easily deduced that the goal or objective of this experiment is to determine the relative density of the liquid L. So basically, what the objective is that we want to get the relative density of kerosene with respect to water. Now let's take a look at how the experiment is going to play out, most likely. The likely experimental setup you should expect on the day of the exam. Here you have your rotor stand, you have your spring balance hanging from a split cup, you have your beaker with the liquid inside, and you have a suspended mass on the spring balance. Now let's take a look at how the experiment is going to proceed. Here you'll be asked to set the mass, the hanging mass, to be, let's say, for example, 20 grams, for instance. Then you'll be asked to dip that mass into water. So this is the mass. This 20, for example, is the mass in air when you've not dipped it anywhere. Then let's say we label water as liquid 1. And let's say we label the kerosene as liquid 2. That is L2, right? And water is L1. We're going to dip that mass in water. And the mass, we're going to record that as M1, right? So in this case, the mass might have dropped by some factor. So that means we may have something like 15, for instance. Typically, when you dip anything in a fluid, let's say water or kerosene or water, you expect the reading of the mass to have reduced. And the reason for that is due to upthrust. Thrust is that force that acts within a fluid. And the force acts upward. It acts in opposite direction to the force of gravity of that object. So in this case, if you dip it in water, you should expect the reading of the mass to have reduced. Okay, now let's talk about the next thing. The next thing is you'll be asked to dip that same mass into another liquid, which is the second liquid, which is kerosene. So let's say by dipping it in kerosene, you're going to get, let's say, 18, for instance, 18 grams. And let's say this is the reading for that liquid too. And that's how the experiment is going to proceed. So what else are you going to be asked to do? You'll be asked to take the difference between M1 and M1, right? If you take that difference, you call that U. So if we take that difference, like that would be 5. Then you'll be asked to take the difference between M and M2. So let's say this is going to give us 2, right? Then the next thing, let's call this one V. That is the difference between M1 and M2. Let's say it's V. The difference between M and M1 is U. Then with all of these values, you'll be asked to repeat this experiment with different values of M. So let's say the first value is 20, the next value might be 50, the next value might be 80, the next value might be 100 grams, and so on. Then you'll be asked to get corresponding values of M1, M2, U, and V. Now, after all of this, what do you think will be the nature of the graph? The graph will be something like this. You'll be asked to plot V against U. So V on the y-axis and U on the x-axis. And that is how the experiment is expected to proceed. And eventually, you'll be asked to calculate your slope and so on and so forth. So the question now is, what should we expect the graph to look like? How is U and V related? What is the single equation that connects U and V? Let's take a look at that. To determine the equation governing this experiment, let's do some labeling. So let's say L1 represents water. So let's say the L2 represents the kerosene, right? And let's say we have the following: the density of water. Let's call that row one. And let's say this is the density of water. And let's say we have row two as the density of L2, that's kerosene. Then let's say we know what M represents. That's the mass in air. Then we know N1 represents the mass in water. And we know N2 represents the mass in the kerosene, that's L2. Now, let's compute the upthrust when in water. So the upthrust when in water, let's say it is W1. Now, upthrust is equal to the mass of the displaced liquid. So if you dip the mass into the beaker, the displaced liquid is equal to the upthrust. Or you can picture it this way: the volume of that mass is also the volume of the displaced liquid. So which means, let's look at it from this perspective. What's the volume of the displaced liquid? So the volume is V. Volume will be constant, whether in water or in kerosene, because the volume of the mass is the same. So whether you dip it in water or in kerosene, the volume will be the same. Then we can calculate that mass as the volume times the density. And the reason why that's the case is density is equal to mass over volume. So if you want to calculate the mass, then you will say the volume times density, that gives you mass. But because we are calculating force, which is the upthrust, we're going to multiply by G. You know, force is mass times acceleration due to gravity, which is G. So that's why this G is going to be present. Okay, this same upthrust is also equal to the difference in the force when it is in air and when it is in water. So what that means is, if I calculate the force, that is the weight, right? When it is in air, that's mg. And when it is in water, that is n1g. The difference is also equivalent to the upthrust, because that that reduction in weight is exactly equal to the upthrust. So you can easily say that we have n minus n1g. Okay, let's do the same computation for the liquid, for L2. So the upthrust in kerosene will be volume, which is constant whether in kerosene or water. The volume of the mass is the same. Then times the density of kerosene times G, and which is equal to N minus N2G. Okay, now let's substitute the U and the V. Since we know that uh, M1, M minus M1G is equal to UG, and M minus M2 is equal to VG. Now we can take this ratio. We can say that we can take this ratio VG divided by UG is equivalent to you taking this ratio. So it's equivalent to the volume, this is capital letter volume, times the density in volume in liquid 2 divided by the same volume. Then we have density in water times G. So if you divide, you end up having this V over U is equal to the density in liquid 2 divided by the density in liquid 1. So we can now see that this is also equivalent to R2. So R2 is the relative density of liquid 2 with respect to the density of liquid 1. Okay, that's fine. So now if you rearrange things, V now becomes R2 times U. So we can see that there's a direct relationship between V and U, and the slope is expected to be the relative density. So your graph should be something like this, where if this is V, and this is u. You should start from zero since the y-intercept is zero, and the slope s should be equal to the relative density of kerosene with respect to water. So this is how you know exactly uh, what connects U and V. And to confirm if whatever you've done is correct, you should expect that your graph should go through zero. And you should know that the relative density of kerosene with respect to water should be the slope. So the question now is, what is the uh, actual value of R2 in the real sense, since you know that the liquid is kerosene? So let me tell you what that is. From fact, we know that the density of kerosene is 810 kilogram per meter cube. And we know the density of water is 1,000 kilogram per meter cube. So the relative density will be 810 divided by 1,000, and that will give you 0.81 as the answer. So you should expect your slope to be 0.81. Now, to wrap up this discussion, what should be your precaution? What are the precautions in this experiment? The first is when taking readings from your spring balance, make sure that you avoid error due to parallax. So don't make sure your eyes is in parallel with the reading that you are taking. Then the second thing is make sure the mass is not touching the bottom of the beaker, otherwise you have false reading. So make sure the mass is actually suspended, not touching the bottom of the beaker. Then another error you should avoid is ensure you avoid zero error. So make sure the spring is reading at zero before you add the mass. So that's all you should need to know about the mechanics for the 2024 physics practical.